Hello everyone, welcome back. Now let's look at section 9.3, hypothesis test for a mean standard deviation unknown. The t-test is a statistical test for the mean of population, and it's used when the population is normally distributed or approximately normally distributed, and sigma is unknown. So that's the most common case. So when we look at a real question, most likely we don't know the population information. So the population standard deviation sigma will be unknown. So it's similar to the confidence interval problem. When sigma is unknown, so we're gonna have a t distribution. Then the only modification we have to do is change that z test statistic to the z to the t1. So now t-test statistic calculated by x bar minus mu over s over square root of n, because we don't have the population sigma. So we replace sigma with s. Then we have a degree freedom equals n minus 1. And then assumptions remain the same. It's unknown, random sample, normally distributed, or n more than 30. So this is guaranteed that we can have a t distribution when sigma is replaced by s. And then now let's look at the example for the still same 5 steps. Step 1, we're going to state the hypothesis and identify the claim. So we have slightly changed. We have a slightly changed example problem this time. So if a company produces bags of peanuts weighing 336 grams periodically, the quality control department takes samples of peanut bags to determine whether the packaging process is under control. That is, to decide if the average weight of the bags has changed. A random sample of 16 bags is taken from the production line and has a mean of 330.91 grams with a population standard deviation with a sample standard deviation of 11 as the average weight increased. So this chapter is mainly about when sigma is unknown. So the information we have, so here's a typo, it's not population standard deviation anymore, with sample standard deviation. And then has the average weight increased at alpha equals 0.01. So those are all the changes we have for this similar example. Then the two possibilities will be it is and more than 336. Then we can write the hypothesis for this updated sample, mu equals 336, and whether it is increased, so mu more than 336. So this is one-sided, or we call it right-sided test, because more than the extreme come from the right end, right tail. So we call it right-sided test. In step 2, we want to find the critical value. So from this example, first thing to look at is alpha, which is 0.01, and to look at the sign of the alternative hypothesis, which is more than. So we have to mention this again, right-tailed. So we draw a bell-shaped curve, which is t now. So centered at 0. So we have an extreme area to the right, which is alpha. Since it's one-tailed, right-tailed, so all the type 1 error or significance level come from right end. So alpha equals 0.01. So this number is going to be t sub 0.01, just t sub alpha. Since it's only one-tailed, we don't do divide by 2 anymore. Then we're going to check t sub 0.01 with degree freedom 15. So this is why we check this one. So we're going to look at our t table. (15) with 0.01. So t sub 0.01 will be this column, and then we find degree freedom 15. So the rating will be 2.602 for that critical value, 2.602. And then we can compare the test statistic. From the example we know, when we assume the null hypothesis H0 is true, mu equals 336. We have our X bar 330.91, the sample standard deviation 11, n equals 16. Then the test statistic equals X bar minus mu naught over S over square root of n. So 330.91 minus 336, which is from here. And 11, the sample standard deviation over square root of 16. So that's negative 1.85. So that's the evidence combined with this assumption, mu equals 336. So now we're gonna make our decision. So compare the evidence with the critical value. So when the evidence is even more extreme than the critical value, to the right side because it's right-tailed more than, then we say we're gonna reject it. And then our problem is our evidence lies in negative 1.85, so it's far away from this rejection region actually. So this is rejection region, and this is negative 1.8, far away from that. So it's less in a regular region, so we cannot say we're gonna reject the null hypothesis. Then we say we fail to reject the null hypothesis. That's the decision. Since 1.85 smaller than that, or we can say it's not more than that. So fail to reject the null hypothesis H naught. Then after we have that decision, the conclusion will be based on the decision. If we fail to reject the null hypothesis, there's not enough evidence. So we're under this scenario. So always in terms of H1. So in this updated example, we fail to reject null hypothesis, indicating there is not enough evidence to conclude the claim. The claim will be the average weight the peanut bags is more than 336 grams at alpha equals. So this is important. Always include this alpha level for the conclusion of the hypothesis testing. Okay, still same 5 steps, and we due to the t distribution, we have slightly different formula here for sigma unknown, and then that is most of the case. So now let's look at the practice problem. So a food company produces bags of peanuts weighing 336 grams. Okay, again, same question, but might be some variation here. Periodically, the quality control department takes samples of peanut bags to determine whether the packaging process is under control, that is, to decide if the average weight of the bags has changed. A random sample of 16 is taken from the production line and has a mean of 330.91 with a standard deviation of 11. That's the sample standard deviation, has the average weight decreased now. So is an alpha change to 0.01. So decrease, that means left-tailed, right? Because you're going to have a smaller than sign. Then step 1, we're going to state the hypothesis. And then we have this curly bracket. First one to state is H naught. It is always mu equals something. And the mu equals what? We got the number from the question, 336. And the alternative hypothesis is H1 is always mu, H1, and then we write down mu. And then the sign is from the claim. The claim is decreased. So smaller than the original number is decreased. So smaller than 336. So that's step 1, to state the null and alternative hypothesis. And then we call it one-sided left tail test. And then after that, we're gonna do our step 2, critical value. To get the critical value, we need to write down the alpha significance level, which is 0.01 given from the problem, and also the sign, which is smaller than, and or we can write down left-tailed, so that we can draw a curve. So now it's a T-curve, and 0 lies in the center, and then the extreme value comes from the left. So the rejection region is from the left because it's left-tailed, and then equals the type 1 error or significance level. So this value is going to be a negative number because it's less to the left of 0. So negative T sub alpha. Negative T sub alpha. So that's negative T sub 0.01. So now we can track the table. Of course, we need to know degree of freedom equals n minus 1 equals n is 16 minus 1, that's 15. T sub 0.01, 15, and that's 2.602. 2.602. So that's negative 2.602 because it's to the left of 0, so it's a negative value now. So don't forget this negative sign to get the correct critical value. So we say the critical value is negative 2.602. And step 3, we're going to get the test statistics. So T equals x bar minus mu naught over S over square root of n. So x bar will be 30.91 minus mu naught, which is 336, divided by 11 over square root of 16. So we're going to calculate that out. So pull out this calculator, type in what we want there. So that's going to be 330.91 minus 336. When we assume mu h naught is true, mu equals 336. And divided by sample standard deviation 11 over 4 square root of 16. So that's negative 1.85. That's the test statistics. And step 4, I'm gonna make a decision. So our decision will be T equals 1.851, and then compare with the critical value. So if it's smaller than the critical value, then we're gonna reject, because smaller than means more extreme than the critical value, the cutoff, because it's left-tailed. So we want to look at even smaller than that. So if that negative 1.85 is smaller than negative 2.602, it's not. So now it's smaller than. So fail to reject. So from this plot, we can also look at that. So we just put negative 1.85 there. So this is negative 2.602. Negative 1.8 should be somewhere here. So it's in a regular region, so it fails to reject the null hypothesis H naught. Then we're gonna look at the last one, step 5. So the decision is always in terms of H0, and then step 5, conclusion, is always in terms of H1. So when we fail to reject it, we're going to say there is not enough evidence because you fail to reject the null hypothesis, and then you kind of in favor of that already. So we cannot support the claim. So not enough evidence. So we're going to say there is not enough evidence to conclude the average weight decrease at alpha equals 0.01. So if you look at this example, 336 is the target number that the quality should be, and then we got a 16 box example, and then we got an average 330.91. If you look at 330.91, the average we got, the evidence, that's actually smaller than 336. But although it seems like it's less than 336, but when you go through the whole testing process, your conclusion will be still that doesn't mean the average weight decreased. So there's still not enough evidence to conclude that. But the truth might be just decreased, but just based on this example now, we still don't have enough evidence to conclude that. That's why we say a conclusion like this. There's not enough evidence to conclude the average weight decreased at alpha equals 0.01. Okay, that's all for this chapter, and then worksheet 9 will be posted.